Hopefully the last video you just watched from Khan Academy just kind of gave you just an overview of why parametric equations are important. Now we're going to kind of switch gears to concrete learning, concrete examples, and what your homework problems will look like. Why don't we consider the path of an object that is propelled into the air that follows a parabolic path? I'm going to give you the equation y equals negative x squared over 72 plus x. We consider this to be a rectangular equation. This is what the graph looks like. Okay. So again, not the most scientific. Sorry, my phone just went off. Not the most scientific, but it's a basic graph where it has intercepts at 0, 0, and 72, 0, and it has a maximum at 36, 18. All right, so you're like, great. That's great, Nat. Rectangular equation, graph, get it. We've dealt with parabolas before. That's nothing special. But what that rectangular equation and graph tells you is it tells you where the object has been. So it can tell you after it's been 18 feet, it's been this height. After it's gone 27 feet, it's been this height. After it's traveled 36 feet, it was at a height of 18. After it traveled after it traveled a distance of 72 feet, it was back on the ground. This equation tells us where the object has been, but it does not tell you when the object was at a given point xy on the path. So in order to determine this time, you can introduce a third variable t called a parameter, hence why these are parametric equations. It is possible to write both x and y as functions of t to obtain parametric equations. Here is the rectangular equation. Here is its corresponding parametric equation, and we will learn how to write this later. Right now, let's just kind of take it in so you can just say, okay, take my word on it, it's true. Okay, so let me show you why it's true. I'm going to show you two ways. One way I'm going to show you is by the equation. I'm going to show you algebraically. If I take this equation and I solve for t, so t is going to equal x divided by 24 over root 2. And now I substitute it into my y equation. I would have y equals negative 16 times x over 24 root 2, the quantity squared, plus 24 root 2 times x over 24 root 2. Okay, I would yield y equals negative 16 x squared. When I put 24 root 2 into the calculator and square it, I get 1152. This 24 square roots of 2, that 24 square roots of 2's cancel, and I'm left with x. And sure enough, if you reduce negative 16 over 11/52, we yield y equals negative x squared over 72 plus x. And we turn the parametric equation into its corresponding rectangular equation. Now let's look at this from a graphical perspective. If I put 0 into the rectangular equation, I would have 0 over 72 plus 0. My output is 0. I'm going to pick nice numbers. I'm going to pick numbers that come on the graph nicely. So when I pick 36, if you pick negative 36 squared over 72 plus x, okay, so if we need to see it, there we go. Negative 36 squared divided by 72 plus 36, I get an output of 18. And then when I put in 72, if I have negative 72 squared divided by 72 plus 72, that yields 0. All right, so we end up with 36, 18, and 72, 0. I'm just taking those 3 points. Now, here is how we determine those same points using parametric equations. When t is equal to 0, in order to find x, I would put 0 in for x. 24 root 2 times 0 is just 0. When I put 0 in for y, I would have negative 16 times 0 squared plus 24 root 2 times 0, which also yields 0. So if I take the coordinate 0, 0, this point right here is occurring at time equals 0. All right, the next number is not intuitive. Again, please take this on just as a beginner example, just so you can understand the relationships on how everything works. I'm going to take t equals 3 root 2 over 4 seconds. So for those of you that need to see concretely, what is 3 over root 2 seconds? All right, let's see if come on. There it goes. Come on, lighting. All right, 3 root 2 divided by 4. Okay, we're looking at approximately little after 1 second, 1.0 seconds. Okay, if I put that into the parametric equation, all right, so if I put it in for x, I would have 24 root 2 times 3 root 2 divided by 4, and that gives us 36. If I take 3 root 2 over 4 and put it into y equals negative 16t squared plus 24 root t, then I would get negative 16, 3 root 2 divided by 4 squared plus 24 root 2 times 3 root 2 divided by 4, and that gives me 18. So at 3618, I've got the same coordinate as I did on the rectangular graph, but this is occurring time equals 3 root 2 over 4, which is approximately 1.06 seconds. So what a parametric equation allows us to do is a couple of things. Not only do we know the horizontal height and the vertical height, but now we know what time it occurs, and we have a direction. We started at time equals 0 here, ended up here, so I know that that is the direction of my object. Okay, last but not least, I'm going to let time equal 3 root 2 over 2. Again, I recognize that's not intuitive. Please just kind of take my word on this first example to just understand the relationships. For those of you that need to see exactly what is 3 root 2 over 2, let's open up a new calculator page so it's clean. I have 3 root 2 divided by 2. So that is approximately right little after 2 seconds. So right around, it looks like it's a glare. It's right around 2.12 seconds. Okay. So again, if I plug it in for my x, if I take 24 root 2 and I multiply it by 3 root 2 divided by 2, I get 72. And if I take 3 root 2 over 2 and put it in for my y coordinate, I would get negative 16, 3 root 2 divided by 2 squared plus 24 root 2 times 3 root 2 divided by 2. And this is the calculator's way of saying 0. Okay, sometimes I know we've had that in class where it's just a calculation. It just couldn't quite get to 0. So notice at 72, 0, I have the same coordinate as I did from the rectangular coordinates, but now I know that this is occurring at 3 root 2 over 2 seconds, which is approximately 2.12 seconds. Again, it also gives me direction. For this particular motion problem that we just discussed, x and y are continuous functions of t, and the resulting path was a plane curve. So just to remember, what we got before was a plane curve. So I'm going to give you the definition of a plane curve, and I am going to refer back to this picture so that you can understand the different parts. So this is the definition of a plane curve. If f and g are continuous functions of t on an interval I, the set of ordered pairs f of t and g of t. So in our previous problem, this right here is considered our f of t. This is considered our g of t. We were given a specific function for x and a specific function for y. Okay, this is considered a plane curve C. The equations given by x equals f of t and y equals g of t are considered parametric equations for C, and t is the parameter. And here we are at example 1. We want to sketch the curve represented by the parametric equation, and we're going to include the orientation or the direction. We're going to confirm our results with the graphing calculator, and we're going to eliminate the parameter and write the corresponding rectangular equation, adjusting the domain when necessary. So here we were given x is equal to t and y is equal to t cubed. So here's how I start this kind of problem. I make myself, when in doubt, t-chart it out. Sorry, again, I forgot to turn my phone off. All right, so we have t, we have x, and we have y. Now, this isn't really in context. So t is a parameter. It doesn't necessarily mean time. So I'm letting you know that just like when I make a normal t-chart, I'm going to let t be -2, -1, 0, 1, and 2 to start with. Again, if this was a context problem, and t truly represented time, I understand that you wouldn't put in -2 and -1. We can't have negative time. But t in this case, this is just a pure math problem. T represents some type of parameter. So when I put -2 and substitute it in for t, I get -2. But when I substitute it into my y equation, I would get -8. When I would substitute in -1 into x equals t, I get -1. When I substitute in my y, -1 cubed is also -1. When I substitute 0 in for x, you're substituting in for the t variable, but for the x function, I would get 0. When I substitute 0 into the y function, I also get 0. When I substitute 1 into the x function, I get 1, 1 into the y, and then I substitute into, and I get 8. So when I go to graph this, I would plot the points -2, -8, -1, 1, 0, 0, 1, 1, 2, 8, and I would graph. And wow, doesn't that look a lot like a cubic? Okay. Now if I want to do this on my graphing calculator to verify, I'm going to press menu and I'm going to open up a graphs page. Okay, now this is in function notation. We have f of 1. So I'm going to go to menu and I'm going to go to graph type, and you want to put in a parametric equation. Okay, so my x1, I'm hoping, let's see if I tilt it, that's a little bit better. So then I get t cubed. And then you'll see that you want from t equals a certain range. So we wanted it from -2 to 2. It tells you that the t step is 0.13. That is really kind of irrelevant. You could make it any step. I always just leave it as the default. And when I graph that, I get the exact same graph that I did by hand. Now, for our last step, let's eliminate the parameter. So we want to take this and we want to rewrite it as a rectangular equation. Well, I already have solved for t. T is already by itself, it's x. So now that I know that t is equal to x, I can substitute it in for this t, and I get y equals x cubed. So here is the rectangular equation, and here was its corresponding parametric. For example 2, it's the same directions. We're going to sketch the curve. We're going to confirm our results with the graphing calculator, and we're going to eliminate the parameter and write the corresponding rectangular equation. The reason I'm doing this example is we're going to have to adjust the domain when necessary. All right, so if I kind of have the same approach as the last problem where I put in -2, -1, 0, 1, and 2, what happens when I try to put -2 in for my x function? Well, in the real number system, that's not in the domain. So in this problem, t cannot equal negative numbers. So when I put in 0, the square root of 0 is 0, and then when I put 0 in here, 1 minus 0 is 1. When I put 1 into the x function, the square root of 1 is 1. When I put 1 into the y function, 1 minus 1 is 0. Now, it's not wrong to put in 2, but let's put in some nice numbers to take the square root of. So I'm going to put 4 in for t. I'm going to be strategic about the numbers I put in. The square root of 4 is 2. 1 minus 4 is -3. And then the last number I'm going to put in is 9 because the square root of 9 is 3, and then 1 minus 9 is -8. So let's go graphing. Okay, I'm going to plot 0, 1. I'm going to plot 1, 0. I'm going to plot 2, -3. And I'm going to plot 3, -8. And I just remembered something I forgot in the last problem. I forgot to indicate the orientation in the last problem. So I'll pull that up here in just a minute. But in this problem, notice how I started here. This is when t equaled 0. This point is when t equals 1. This is when t is equal to 4. This is when t is equal to 9. And so this is the direction if an object was moving along that path. If I pull up the previous problem, we know that at -2, 2, this is when t was equal to -2, t is equal to -1, t is equal to 0, t is 1, and t is 2. So this would be the orientation of my parametric graph. Okay, just want to make sure I cleared that up. All right, so moving forward, let's go ahead and confirm our results with the graphing calculator. Okay, sorry, I'm tilting it a little bit because the glare is kind of bad. So again, I'm going to hit menu, and I'm going to go down to graph type, and I want to put in a parametric. Okay, and if I notice, my parametric for my x is the square root of t. My y is 1 minus t. And we put in values, just so that we can verify our results, we put in values from 0 to 9. Again, I'm leaving the t-step as my default. And notice how I get a graph that is the exact same as the one that we got by hand. Okay, so now that we have verified our results, our last thing to do is to eliminate the parameter and put this in as a rectangular equation. So I've got x is equal to root t. Well, in order to get t by itself, I would have to square both sides. So t is equal to x squared. So now I need to use y equals 1 minus t and substitute. So I get 1 minus x squared as my rectangular. But notice my x values are not going to be bigger than 0. So I have to put a domain restriction that x has to be greater than or equal to 0. You now have enough skills to try learning opportunity number 1, which is starting on page 673, 1 to 17 on. Good luck.